This video is a continuation of the mean value theorem. And what we're looking at now are two corollaries or sort of extensions of the mean value theorem. The first one is saying that if the derivative of a function equals 0 on the entire interval, then the original function has to be a constant function. This is kind of going backwards from the way that we have thought about things. We've gone the other way where we said if a function is a constant and the derivative is 0, what we're doing now is going the other direction. If the derivative is 0, then we know that the original function was a constant. So that's the first one. I'll prove these separately. We want to show that f has a constant value between a and b. So let's just choose two different points. Let's choose x1 and x2 somewhere in the interval. And let's just say, just to have them in order, that x1 is less than x2. Just want to put them somewhere on the number line. And we want to show that f of x1 is equal to f of x2. We're picking two arbitrary points, and if we can show that their y values are equal, that means that the function has to be constant. Our original assumptions satisfy the hypotheses of the mean value theorem, that it's a continuous function and that they're differentiable. So we know that there's some point c in between x1 and 2 where the derivative is equal to 0. So let's say we know by the mean value theorem that there is some point C where the derivative is equal to the slope between those two lines, right? F of x2 minus f of x1 over x2 minus x1. Somewhere the derivative is equal to the slope of that secant line. But we just said in one of our assumptions that this is 0 everywhere. So what I'll do is I'll say, okay, well then 0 has to be this. We made an assumption that x2 and x1 are different. So we know that the denominator, and we have to have that, so the denominator doesn't equal 0. So this means then that f of x2 has to equal f of x1, right? Because that has to be equal to 0. This part here has to equal to 0, so those two have to be equal to one another. Well, that's what we're trying to show. If the two y values are equal, then we know that the function is constant. So we've proved the first corollary. Back at the second corollary, it's saying that if we have two different functions that have the same derivative on some interval, then there's a constant function, c, such that if you add that to one of the functions, you'll get the other function. Looking at this picture over here on the right, it's saying that the two functions look identical on that interval, but that they are just vertical shifts of one another. And again, we can show this the opposite way. We could show by taking derivatives that say x squared plus 2 and x squared minus 1 have the same derivative. But we're trying to go in the opposite direction and say, if they have the same derivative, what did the original functions look like? Both of these corollaries are going to lead us to the technique of integration, where we're taking a function and working backwards to find what its derivative, to find a derivative and go back to find the original function. So let's prove corollary 2. So let's define a new function, h of x, and we'll have it be f of x minus g of x. And we're going to say that this is good for all x's in the interval between a and b. Well, taking the derivative here, we can just have this. And we know that this has to equal 0 because these two things are equal to each other. So then we're saying that h prime of x equals 0. But then if we apply corollary 1, we can say that h of x equals some constant and then, kind of putting this all together, f of x minus g of x, making the exchange for h of x, is some constant. And then moving the g of x over, we get that f of x is equal to g of x plus c. Here's an example function of an example problem. Suppose that we want to find a function that has a derivative of sine of x and that passes through a particular point. So what we're saying is we want to have the slope be something in particular, and we want it to pass through a particular point. Let's find the function that meets that criteria. So let's call our function g of x. Thinking about what we know about derivatives of trig functions, what happens if we let g of x equal negative cosine of x? I think that then if we took the derivative here, we'd have negative sine. That would give us sine of x, so that's what we want. We want our g of x to be defined that way. So this original function, f of x, f of x and g of x, this new one we just found, have the same derivative. So thinking about corollary 2 that we just found, we know that f of x has to be g of x potentially plus some constant, or negative cosine x plus c. We know that the graph is going to pass through the point 0, 2. So let's plug that in. F of 0 is going to be negative cosine of 0 plus c, or 2 is equal to cosine of 0 is this is going to be negative 1 plus c. So I'm getting that 3 is equal to c. So that means that the function that we were looking for, f of x, is going to be negative cosine of x plus 3. All right, that is all that I have. We'll do more examples in class, and thanks for watching. Have a great day.